Hello everyone, I'm Professor Harrison and welcome back to our module on statistical inference. Today we're going to be talking about type 1 and type 2 errors. These are two distinct ways a hypothesis test can give you the wrong answer. We're following Bess. She's an investigative journalist on a cold case she can't let go. Today she's covering a story about a regulatory fraud detection algorithm that flagged a trader for insider trading. The question she's trying to answer is whether the algorithm got it right. The algorithm flagged the trader. An investigation followed, and investigators cleared the trader. But the case didn't quietly go away. She pulls up her case file. A hypothesis test gives you a decision. Reject the null or fail to reject it. We've covered how to make that decision. We know we can use significance levels, p-values, and things like the decision rule, but what we haven't figured out yet is the two ways that that decision can go wrong. There are exactly two errors that you can make, and they point in opposite directions. They also carry completely different consequences depending on your context. The first type of error is called a type 1 error. A type 1 error is what happens when you reject the null hypothesis and the null hypothesis is actually true. In this circumstance, you concluded that something was actually happening when something actually wasn't. This is basically just a false positive. The probability of committing a type 1 error is exactly equal to your significance level alpha. So when you set alpha equal to, for example, 0.05, you're accepting a 5% chance of falsely rejecting the null hypothesis. That tolerance ends up being baked into it by design. It's not a flaw in the test. It's a deliberate choice of how often you're willing to be wrong in that direction. Going back to Bess's case, the algorithm tests each trader against a null hypothesis, that the trader's activity is consistent with normal market behavior. The alternative is that the pattern is inconsistent enough to suggest insider trading. What happened is that the algorithm set its threshold, ran its test, and ended up flagging a trader. A type 1 error here would mean that the algorithm concluded that insider trading was happening when the trader was actually trading cleanly. The null hypothesis was actually true, and the person was innocent. The test rejected it anyway, however. A real person ends up getting investigated in this circumstance, and their career might end up taking a hit, they might face legal consequences, and in the end, the case ends up falling apart in court. The regulator ends up taking the credibility hit on that too. The reason being, an innocent trader was accused, and a lot of resources were wasted trying to get the innocent trader convicted. The second type of error that could end up happening is a type 2 error. A type 2 error is what happens when you fail to reject the null hypothesis, and the null hypothesis is actually false. In this circumstance, something was actually going on, and the test just missed it. So we have a false negative. The probability of a type 2 error carries a specific label, which we'll call beta. In Bess's case, a type 2 error means that an actual insider trader passed through the algorithm undetected. So the null here was false, but real insider trading was happening behind the scenes and the test didn't flag it. So here the victim takes losses and no one gets caught. So which error here is worse? Well, that depends entirely on the stakes. In a regulatory context, a type 2 error lets a criminal go undetected. In a medical testing context, a type 1 error might send a healthy patient through a harmful treatment. Neither is universally worse. The consequences determine which direction of mistakes you're more willing to accept. So here's the trade-off. Because alpha directly controls type 1 errors, reducing your tolerance for false positives means you need more evidence before you're willing to reject the null. Needing more evidence means you'll miss more real effects. You'll end up with more type 2 errors. Tighten the standard on one side and you loosen it on the other. That trade-off is structural, and it comes from the shape of the decision rule itself, not from any failure of execution. So when the regulatory algorithm was tuned towards avoiding false accusations with a low alpha and a strict threshold, it became more likely to miss real violations. That's a deliberate choice about which kind of error the agency was more willing to tolerate. Both kinds are still possible, and the significance level just decides which one you've pushed down and which one you've let rise. In her article, Bess explains this to her readers. The algorithm cleared the trader, but clearing someone statistically and clearing someone in truth are not the same thing. The agency set a strict standard, strict enough to protect the innocent, but in exchange it wasn't a loose enough rule so some of the guilty may have walked free. So that's type 1 and type 2 errors. Every hypothesis test has exactly two ways of being wrong. A type 1 error is rejecting a true null. That's a false positive, and the probability of that happening is alpha, your significance level. A type 2 error is failing to reject a false null. That's a false negative, and its probability of happening is called beta. Lowering alpha reduces type 1 errors but drives up type 2 errors. You can't reduce both at the same time without more data. And that trade-off is exactly what we're going to cover next.